Welcome to the series of e-learning modules on critical path identification, slack time and float. By the end of this session, you will be able to determine critical path, identify floats associated with non-critical activities and events, and finally to explain total project completion time. Now let us start with an introduction. Critical path is the longest path through the project network. The activities on the path are the critical activities. Therefore, any delay in their completion must be avoided to prevent delay in project completion. The objective of critical path analysis is to estimate the total project duration and to assign starting and finishing times to all the activities involved in the project. This helps to check the actual progress against the scheduled duration of the project. The duration of individual activities may be uniquely determined, that is, in case of CPM, or may involve the 3 time estimates in case of PERT, out of which the expected duration of an activity is computed. Having known this, the following factors should be known in order to prepare the project scheduling. First is the total completion time of the project. Second, earlier and latest start time of each activity. Third, the critical activities and critical path. And lastly, the float for each activity, that is, the amount of time by which the completion of a non-critical activity can be delayed without delaying the total project completion time. Coming to notations, events and calculations. Consider the following notations for the purpose of calculating various times of events and activities. E of I is the earliest occurrence time of an event I. This is the earliest time for an event to occur immediately after all the preceding activities have been completed without delaying the entire project. L of I is the latest allowable time of an event I. This is the latest time at which an event can occur without causing a delay in already determined project's completion time. Es of Ij is the early starting time of an activity Ij. This is the earliest time an activity can possibly start without affecting the project completion. Ls of Ij is the late starting time of an activity Ij. This is the latest possible time an activity can start without delaying the project completion. Ef of Ij is the early finishing time of an activity Ij. This is the earliest time an activity can possibly finish without affecting the project completion. Lf of Ij is the late finishing time of an activity Ij. This is the latest time an activity must finish without delaying the project completion. T of Ij is the duration of an activity Ij. It has already been mentioned that in a network diagram, there should only be one initial event and one end event. The other events are numbered consecutively with integer 1, 2 up to n such that I is less than j for any two events I and j connected by an activity which starts at I and finishes at j. For calculating the earliest occurrence and latest allowable times of events, the following two methods are used, that is, forward pass method and backward pass method. Forward and backward pass method. Firstly, let us understand the forward pass method. This is for the earliest event time. In this method, calculations begin from the initial event 1, proceed through the events in an increasing order of event numbers and end at the final event, say n. At each event, we calculate its earliest occurrence time E and the earliest start and finish time for each activity that begins at that event. When calculations end at the final event n, its earliest occurrence time gives the earliest possible completion time of the entire project. The method may be summarized as follows. First, set the earliest occurrence time of initial event 1 to 0, that is, E1 is equal to 0 for I equal to 1. Second, calculate the earliest time for each activity that begins at event I equal to 1. This is equal to the earliest occurrence time of event I, that is the tail event, that is, Es of ij is equal to E of I for all activities ij starting at event I. Third, calculate the earliest finish time of each activity that begins at event I. This is equal to the earliest start time of the activity plus the duration of the activity, that is, Ef of ij is equal to Es of ij plus T of ij equal to E of I plus T of ij for all activities ij beginning at event I. Fourth, proceed to the next event, say j being greater than I. Fifth, calculate the earliest occurrence time for the event j. This is the maximum of the earliest finish time of all activities ending into that event, that is, E of j is equal to max of E of I plus T of ij for all immediate predecessor activities. Sixth, if j is equal to n, that is the final event, then earliest finish time for the project, that is, the earliest occurrence time E of s for the final event is given by E of n is equal to max of Ef of ij equal to max of E of n minus 1 plus T of ij for all terminal activities. Now coming to the backward pass method. This is for the latest allowable event time. In this method, calculations begin from the final event n. Proceed through the events in the decreasing order of event numbers and end at the initial event 1. At each event, we calculate the latest occurrence time L and the latest finish and start time for each activity that is terminating at that event, and this procedure continues till the initial event. The method may be summarized as follows. Firstly, to set the latest occurrence of last event n equal to its earliest occurrence time, known from the forward pass method, that is, L of n is equal to E of n, j is equal to n. Second, calculate the latest finish time of each activity which ends at event j. This is equal to latest occurrence time of the final event, that is, Lf of ij is equal to L of I for all activities ij ending at event j. Third, calculate the latest start times of all activities ending at j. This is obtained by subtracting the duration of the activity from the latest finish time of the activity. That is, Lf of ij is equal to L of j and Ls of ij is equal to Lf of ij minus T of ij equal to L of j minus T of ij for all activity ij ending at event j. Fourth, proceed backward to the event in the sequence that decreases j by 1. Fifth, calculate the latest occurrence time of event I, where I is less than j. This is the minimum of the latest start times of all activities from the event. That is, L of I is equal to minimum of Ls of ij equal to min of L of j minus T of ij for all immediate successor activities. Sixth, if j is equal to 1, that is the initial event, then the latest finish time for the project, that is latest occurrence time L of I for the initial event is given by L1 is equal to min of Ls of ij is equal to min of L of j minus 1 minus T of ij for all immediate successor activities. Now, next coming to float of an activity and event float, that is slack of an activity and event. The float or slack or free time is the length of time in which a non-critical activity or an event can be delayed or extended without delaying the total project completion time. Coming to slack of an event. The slack, also called float of an event, is the difference between its latest occurrence time, that is L of I, and its earliest occurrence time, which is E of I. That is, event float is equal to L of I minus E of I. It is a measure of how long an event can be delayed without increasing the project completion time. If L is equal to E for certain events, then such events are called critical events. If L is not equal to E for certain events, then the slack on these events can be negative, that is, L is less than E, or positive, that is, L is greater than E. Slack of an activity. It is the amount of time that an activity can be delayed without delaying project completion. It is calculated as the difference between the latest finish time and the earliest finish time for the activity. In other words, the computation of activity floats tells us how long an activity time may be increased without increasing the project completion time. Mainly, three types of floats are defined for each non-critical activity of the project. The first is total float. This is the length of time by which an activity can be delayed when all preceding activities are completed at their earliest possible time and all the successor activities can be delayed until their latest permissible time. The time within which an activity must be scheduled is computed from Ls and Es values for each activity start event and end event. That is, for each activity ij, the total float is equal to the latest allowable time for the event at the end of the activity minus the earliest time for an event at the beginning of the activity minus the activity duration. That is, total float Tf of ij is equal to L of j minus E of I minus T of ij equals to Ls of ij minus Es of ij equals to Lf of ij minus Ef of ij. Next is free float. For calculating the total float, only a particular activity was considered with respect to its tail and head event occurrence times, or by considering latest start and finish time of an activity with respect to its earliest start and finish time. However, we may need to know how much an activity's completion time may be delayed without causing any delay in its immediate successor activities. Thus, the free float of a non-critical activity is defined as the time by which the completion of an activity can be delayed without causing any delay in its immediate succeeding activities. Free float values for each activity ij are computed as follows. Free float ff of ij is equal to E of j minus E of 1 minus T of ij is equal to min of Es of ij for all immediate successors of activity ij minus Ef of ij. Now, next coming to independent float. This is the amount of acceptable delay in the completion of an activity so that it neither affects its predecessor nor the successor activities. Thus, independent float is the amount of time available when preceding activities are completed at their latest permissible times and all the following activities can still be completed at the earliest possible time. Independent float values for each activity are computed as follows. Independent float if of ij is equal to E of j minus L of I minus T of ij equal to Es of ij minus Ls of ij minus T of ij. The negative value of independent float is considered to be 0. Now let us have a view of the remarks. Latest occurrence time of an event is always greater than or equal to its earliest occurrence time. That is, L of I is greater than or equal to E of j. Tf of ij is greater than or equal to E of I minus E of j minus T of ij, or Tf of ij is greater than or equal to Ff of ij. This implies that the value of free float may range from 0 to total float and can never exceed the total float value. Thus, independent float is less than or equal to free float is less than or equal to total float. Secondly, the calculation of various floats can help the decision maker in identifying the underutilized resources, flexibility in the total schedule and the possibilities of redeployment of resources. Third, once the float of an activity is disturbed, the float of all other activities of the project is changed and should be recalculated. Fourthly, few conclusions which can be drawn from the total float value of an activity are as follows. The total float value is negative when L minus E less than 0, project completion is behind the schedule data, that is, the resources are not adequate and activity may not finish in time. This needs extra resources or certain activities need crashing in order to reduce negative float value. The total float value is 0 when L minus E is equal to 0. Resources are just sufficient to complete the activity. Any delay in activity execution will necessarily increase the project cost. Total float value is positive when L minus E is greater than 0. Project completion is ahead of the schedule date, that is, resources are surplus. These resources can be deployed elsewhere or execution of the activity can be delayed. Now coming to critical path and its example. First, what is critical path? Certain activities in a network diagram of a project are called critical activities because delay in their execution will cause further delay in the project completion time. Thus, all activities having 0 total float value are identified as critical activities. The critical path is the sequence of critical activities that form a continuous path between the state of a project and its completion. This is critical in the sense that if any activity in these sequences is delayed, the completion of the entire project will be delayed. The critical path is shown by a thick line or double lines in the network diagram. The length of the critical path is the sum of the individual times of all the critical activities lying on it and defines the longest time to complete the project. The critical path of a network diagram can be identified as, for all activities ij lying on the critical path, the E values and L values for tail and head event are equal. That is, E of j is equal to L of j and E of I is equal to L of I. On critical path E of j minus E of I is equal to L of j minus L of I is equal to T of ij. Finding the critical path is important for directing the decision maker's attention because Delay in any one of these activities will increase the project completion time. Now let us take an example to understand the concept we have now learnt. An established company has decided to add a new product to its line. It will buy the product from a manufacturing concern, package it and sell it to a number of distributors that have been selected on a geographical basis. Market research has already been indicated the volume expected and the size of the sales force required. The steps shown in the following table are planned. In the table, first column indicates the activities and second column indicates the description of the respective activities. Third column indicates the predecessors for each activity and fourth column represents the duration taken to complete the individual activities. The precedence relationship among these activities are shown in the following figure. As the figure shows, the company can begin to organize the sales office, design the package and order the stock immediately. Also, the stock must be ordered and the packing facility must be set up before the initial stocks are packaged. Draw an arrow diagram for this project, indicate the critical path and for each non-critical activity, find the total and free float. The arrow diagram for the given project along with the E values and L values is shown in the figure. Let us determine the earliest start time E of I and the latest finish time L of j for each event by proceeding as follows. First, the forward pass method. E1 is equal to 0, E2 is equal to E1 plus T1, 2 is equal to 0 plus 6 is equal to 6. E3 is equal to E1 plus T1, 3 is equal to 0 plus 2 is equal to 2. E4 is equal to max of EI plus Ti, 4 is equal to max of E1 plus T1, 4, E3 plus T3, 4 where I is equal to 1, 3 which is equal to max of 0 plus 13, 2 plus 10 is equal to 13. E5 is equal to E2 plus T2, 5 is equal to 6 plus 4 is equal to 10. E6 is equal to max of EI plus Ti 6 where I is equal to 2, 5 is equal to max of E2 plus T2 6. E5 plus T5 6 is equal to max of 6 plus 9. 10 plus 7 is equal to 17. E7 is equal to E2 plus T2, 7 is equal to 6 plus 2 is equal to 8. E8 is equal to E7 plus T7, 8 is equal to 8 plus 4 is equal to 12. E9 is equal to max of EI plus T1 Ti 9 where I is equal to 4, 6 is equal to max of E4 plus T4 9. E6 plus T6 9 is equal to max of 13 plus 6. 17 plus 3 is equal to 20. E10 is equal to max of EI plus Ti 10 where I is equal to 8, 9 is equal to max of E8 plus T8 10. E9 plus T9 10 is equal to max of 12 plus 10. 20 plus 5 is equal to 25. Backward pass method. L10 is equal to E10 is equal to 25. L9 is equal to L10 minus T9, 10 is equal to 25 minus 5 is equal to 20. L8 is equal to L10 minus T8, 10 is equal to 25 minus 10 is equal to 15. L7 is equal to L8 minus T7, 8 is equal to 15 minus 4 is equal to 11. L6 is equal to L9 minus T6, 9 is equal to 20 minus 3 is equal to 17. L5 is equal to L6 minus T5, 6 is equal to 17 minus 7 is equal to 10. L4 is equal to L9 minus T4, 9 is equal to 20 minus 6 is equal to 14. L3 is equal to L4 minus T3, 4 is equal to 14 minus 10 is equal to 4. L2 is equal to min of luminous T2 j where j is equal to 5, 6, 7 is equal to minimum of L5 minus T2, 5, L6 minus T2, 6, L7 minus T2, 7 is equal to min of 10 minus 4, 17 minus 9, 11 minus 2 is equal to 6. L1 is equal to min of Lj minus T1 j, where j is equal to 2, 3, 4 is equal to min of L2, T1 2, L3 minus T1 3, L4 minus T1 4 is equal to min of 6 minus 6, 4 minus 2, 14 minus 13 is equal to 0. The critical path in the network diagram has been shown. This has been done by a dark line joining all those events where E values and L values are equal. The critical path of these projects is 1, 2, 5, 6, 9, 10 and critical activities are A, B, C, L and M. The total project time is 25 weeks. For each non-critical activity, the total float and free float calculations are shown in the table. In the first column, we have shown the activity. The second column indicates the duration taken by each activity. The third column shows the earliest start time and finish time. Earliest start time as calculated earlier is taken. The earliest finish time is the total of the earliest start time plus the duration of each activity. The fourth column indicates the latest start time and the latest finish time. Latest start time is the latest finish time minus duration. Latest finish time is also calculated and taken. The next column indicates both the total float time and the free float time. Total float time is the difference between the latest finish time minus the duration and the result minus earliest start time. The free float time is the result of the difference of the earliest finish time and earliest start time minus the duration time of the activity. Now coming to the summary of the topic. Here's a summary of our learning in this session where we have understood how to determine critical path and also to identify floats associated with non-critical activities and events, and finally the total project completion time. Thank you.